Hi everyone, in this video we're going to be looking at how to calculate thermal energy changes when two substances are put together. In other words, we're looking at the famous mixture questions. So I thought I'd quickly review a couple of important definitions. So we're going to look at thermal energy. So remember, thermal energy is the total energy of all particles. It's the potential and kinetic energy total for a particular substance. And then we also looked at temperature, which is the average EK of the individual particles. And here's the famous example we did the other day, where we looked at a bathtub filled with cold water and a small container of hot water. And what you can see is that the individual particles in the bathtub have a low relative energy compared to those in the beaker. So this represents temperature. So the temperature is much, much lower because you have a lower average EK per particle here. However, when you look at the total energy in the bathtub, we add all of these up, you end up with 100 joules. So even though each particle has less energy, because there's so many of these particles, they more than offset that, and as a result we have lots more thermal energy in the cooler water here, believe it or not. And then we had this example we looked at today in class where we have two beakers, A and B. They're both at the same temperature, and the question was, compare the thermal energy. Well, B obviously has much more thermal energy because it has more particles. The greater the mass, the more particles, and therefore the more total energy that's present. And what happens after you mix the two substances together, A and B? Well, they're the same temperature. Both beakers have the same type of particle in terms of energy content. And when you look at the total energy, the thermal energy of A and B, when you mix them together, the total in this final mixture will be the sum of the individual beakers here. So there's no change really overall in energy. Things change when we've got two different temperatures. So we have here, we've got beaker B, which is at 95 degrees Celsius. And what's going to happen is it's going to cool off when you mix them together. And beaker A at 21, it's going to warm up. And here we're going to be assuming a complete transfer, 100% efficient transfer of energy from the water in B to the water in A. Now, when you think about it, because it's a constant, or the same amount of water in each beaker, the final temperature will be intermediate between these two temperatures. So it should be around 58 degrees. So what's going to happen is thermal energy will go from B to A, and we can actually calculate that energy. So what we can do is we can figure out how much energy change there is associated with this temperature change using the MCAD equation. So remember, the MCAD equation is the change in thermal energy is equal to the mass times the heat capacity times the change in temperature for that particular substance. So let's check out beaker A. So beaker A, remember, it has water at 21 degrees Celsius, mass of 225 grams. So you have to remember that each gram of water is really a milliliter of water, and this represents 0.001 kilograms. So in other words, each milliliter is 0.001 kilogram, and here we've got 0.225 kilograms as a result. Now the initial temperature of the water in the cool beaker is 21, and remember, the final temperature, when you mix everything together, will be 58. So we're looking at the temperature change. So be careful. That's what this delta T is. It's not the temperature difference. So here, when you look at it, it's going to be TF minus TI. So we have an increase of 37 degrees Celsius. And you plug it into the equation here. We've got our mass, specific heat capacity of water, temperature change, and we find that beaker A gained 35,000 joules of thermal energy. Well, let's look at beaker B. Now beaker B, remember, it was a little different. It had the same amount of water, but it was at 95 degrees Celsius. So what happened here is the temperature is going to go down. We have a temperature decrease of 37 degrees. So when you calculate the energy change, it's going to be the mass times the specific heat capacity times this temperature change, which gives you a negative change in energy. It makes sense. This beaker was very, very hot. It cooled off. As a result, it lost this much energy. The other particles in the other beaker, they gained that energy. So this is really a specific example of law of conservation of energy. So it's very interesting. So we call this the principle of heat exchange. And again, what's happening when you have two different substances mixed together? The cold substance gains thermal energy, the hot substance loses the thermal energy. We can calculate the amount gained and loss. It should be equal on either side. So let's look at another example here. So here, we don't know the final temperature because the masses aren't consistent here. We have quite a bit more of the hotter water. So we're going to figure out the final temperature of this mixture here. So again, we're mixing these two containers and get this mixture. And what is the final temperature here? We don't know. So TF, the question mark. All right, so what we do know is this. We know that the mass of the water is 125 grams. We have the heat capacity of water, and we know the temperature change is going to be the final minus 21 degrees here, the starting point. We don't know what TF is, but that's okay. And then same thing with beaker B. It starts at 95 degrees, and we're going to have our final temperature, again, which we don't know. We also know the mass here. So what we do know is that beaker A, the cooler beaker, is going to gain the energy, so we put a positive sign in front here. Beaker B, it's hotter, it's going to lose the energy, so put a negative sign here. We've got our MCAT on either side. Mass, heat capacity, there's my temperature change, TF minus 21. Same thing on this side, being careful to keep the negative sign in front. So mass, heat capacity of water, TF minus 95 in this case. Let's simplify factors in the front. So this ends up being 522.5 on the cold side. We multiply it through, FOIL. We end up with 522.5 TF minus 10,972.5. On this side, be careful, negative 1045 times TF gives you a negative 1045 TF. Negative 1045 times negative 95 gives you a positive 99,275. And what we're going to now do, we're going to bring the negative values onto the opposite side. So the 1045 TF becomes positive, and the 10,972 becomes positive when you bring it over here. We clean it up a little bit, and we end up with a final temperature of 70 degrees Celsius. So there you go. So the final temperature of this mixture, 70. So again, what we did, we created the two sides. We know that we lose energy on this side. We gain it on this side. Careful with your temperature changes. TF minus 21, TF minus 95, and we got our final answer. Here's another example where we don't involve water. So in this case, we're going to be placing a hot piece of iron into a container of water at 21 degrees Celsius. The same rules are going to apply. We're going to be taking the energy from the iron. It's going to be transferring over into the water. So we're going to have a negative energy change here. And the thermal energy we lose there is going to be gained by the water. So we have our values here, being careful to look up the heat capacity for iron, which is 450 joules per kilogram degrees Celsius. First page of your workbook, of course. We have our final temperature, TF minus 95. On this side for the water, TF minus 21. Remember, the iron loses, it's negative in front here. The water gains, so we have a positive there. And basically through math, the same rules apply just like before. We plug the values in, we do the FOIL, then we isolate for TF, and we have a final temperature of 25 degrees for the mixture, which is kind of interesting. Does that make sense? Well, let's check it out. Remember, the iron was 95 degrees before we put in the water, and then the mixture was 24 degrees. That's a significant change in temperature, 71 degrees Celsius change in temperature. Look at the water. It only went up by 4 degrees. So the cool water went up by 4 degrees. The iron went down by 71 degrees. Why? Remember, heat capacity. Iron has a very, very low heat capacity. So even though it's at a high temperature, it doesn't have very much thermal energy. And when it gives that thermal energy to the water, it doesn't do very much because the water needs a lot of energy in order to change its temperature. It has a very, very high heat capacity. So does this answer make sense? Yes, of course it does. So folks, that's it. Try some of the other calculations you have in the workbook. Here they are. You also have a video corresponding to this on the website. Take care. Have fun with these.